First of all, thanks to the organizers for inviting me. This has been a really cool conference so far. So yeah, I want to talk about Koszul property symbolic powers of cover ideals. This is joint work with Yan Gu and my advisor Tai Ha. It's going to follow a basic math talk design of tell you what I'm talking about, why I'm talking about it, and what I did with it. My results at the very end are super technical, so I'm going to mostly hand wave over them. If you have questions, feel free to ask. I've also done a whole bunch of pictures of examples and stuff, so that should be helpful. So let's get into it. So first I'm going to talk about cover ideals. So cover ideals are related to graphs. When I talk about a graph, I'm just talking about a bunch of nodes with edges between them. Over the vertex set x1 to xn, and the cover ideals will be subsets, will be ideals of the ring, of the polynomial ring. So a cover ideal in general is a really basic definition. So just take any edge of your graph, make the two vertices of that edge an ideal, and then intersect all of those ideals. And that's your cover ideal. And it's called a cover ideal because each generator of this ideal associates to a vertex cover. To see what that all looks like. So here's a graph. So each edge here you can see, so x1, x2, you get that ideal, x2, x3, you get that ideal, x3, x4, you get that ideal, so on and so forth. And when you intersect all of them, you get this, and each generator is a vertex cover. So that means each edge touches one of these vertices. And then each edge touches one of these vertices. So that's the second generator. And then each edge touches one of these, which is the last generator. So that's a cover ideal. What I do with them is I take symbolic powers of these ideals. So symbolic power, the way you find it in general, is you take the ordinary power of the ideal, multiply it by the localization of the ring localized over some associated prime, intersect that with the original ring, and then intersect all of those across all associated primes. It is very hard to calculate, even for computers, even for something as simple as a cover ideal. You can't get very big graphs or very big powers. For square-free monomial ideals like cover ideals, we have a slightly simpler definition, which is just taking the associated primes to ordinary powers and intersecting those. So it is a little bit easier, but still can be very, very complicated very, very quickly. So as an example, as I said before, the cover ideals associated primes correspond to edges of the original graph. So each one of those edges is a prime. So cover ideals are already defined using their associated primes. Finding the symbolic power of the cover ideal is as simple as taking each one of these, raising it to the ordinary power, and then intersecting. And you get this, which got real gross real fast and lost a lot of really nice properties. That's basically how symbolic powers work. And they have lots of applications across various parts of algebra, which I won't go into because they get very complicated very quickly. So a property I'm interested in when I'm looking at graphs is vertex decomposability. So a graph is vertex decomposable if it's totally disconnected, which just means it's just vertices and no edges. If otherwise, there has to be some vertex when I delete the vertex, and when I delete the neighbors of the vertex, I get something that's vertex decomposable. And when no independent set of the deletion of the neighbors is maximal when I delete just the vertex. So this property, I ran out of room. If X meets that property, you call it a shedding vertex. So as an example, here we have C4. So C4 is not vertex decomposable. This is usually easier to see when something is not vertex decomposable than when it is. And it fails the second condition. So if I delete X1, I get a path that's vertex decomposable. If I delete the neighbors of X1, I just get X3. That's an isolated vertex, so it's vertex decomposable. But the reason this fails is X3 is the only independent set in the deletion of the neighbors, so here. But X3 is maximally independent when I delete just X1. So it can't, this graph is not vertex decomposable. So you can do something called whiskering a graph. And what you do with whiskering is basically you introduce this new vertex Y and then connect it to whatever vertex you want to whisker. And that's essentially what this process is. And if you want to talk about whiskering a set of vertices, you just introduce a vertex, you just introduce a Y for each vertex in that set and then connect it one by one. And what's cool about whiskering is it forces this vertex to be a shedding vertex. So automatically X1 is now a shedding vertex. That second property is met. Which is super useful because that second property is actually like what makes, in a lot of cases, not always, what makes vertex decomposability really hard. So why do I care? Why am I talking about graphs and cover ideals and symbolic powers and all this stuff? One is Koszul modules. So Koszul algebras were introduced by Priddy in the 70s and were generalized to modules by Herzog and Iyengar. And a finitely generated R module is called Koszul if its associated graded module, that thing, with respect to the maximal ideal M, has linear resolution over the associated graded ring. So this is a really nice property. It is related to a whole bunch of other properties too. One is the Golod property. So it's Golod if the Koszul complex of R mod I admits trivial Massey operations. And this is also, Golod is immediately linked to symbolic powers because Herzog and Hünecke showed that homogeneous ideal, if you have a homogeneous ideal, then its ordinary and symbolic powers are Golod. And then another related property is component-wise linearity. So if each degree component, if something is component-wise linear, if each degree component has linear resolution. So this is another related property to Koszul property, to the Koszul property. I'll show how everything is linked here in a second. But so for this one thing, we get sort of two related properties. And a third biggie is sequentially Cohen-Macaulay. So if you've ever heard of a Cohen-Macaulay graph or a Cohen-Macaulay ideal, this is the non-pure version of that. And basically, something is sequentially Cohen-Macaulay if there is a filtration of R modules such that the dimension of the quotients increase and the quotients are Cohen-Macaulay. So these relate to graphs because in 1990, Villarreal showed that if you whisker all the vertices of a graph, then that graph is Cohen-Macaulay. And then Francisco and Ha in 2008 showed that if you whisker a certain subset of vertices, so when either it's chordal or C5, then that graph is sequentially Cohen-Macaulay. So the first, Villarreal showed Cohen-Macaulay, which is a slightly stronger thing. And then Francisco and Ha showed a sequentially Cohen-Macaulay by whiskering a subset. So we get a slightly looser restriction and a slightly looser result. What brings all of this together and why I'm talking about all these various different things. So in 2009, Woodruff showed that vertex decomposability implies sequentially Cohen-Macaulay. Yanagawa and Romer independently showed that a homogeneous ideal is Koszul if and only if it's component-wise linear. Then Herzog and Hebe and Yanagawa each showed that the cover ideal is component-wise linear if and only if the graph is sequentially Cohen-Macaulay. So here's what this all looks like. We have this. What I basically want to do is do this. Show that whiskering a certain subset forces vertex decomposability, and then I get all the cool stuff that I want. So the question is, can I whisker a graph in such a way that the symbolic powers of the cover ideal are Koszul? The answer is, yeah, in certain situations. So here are a few previous results. Quick question. I got to stop at 320, right? Cool.
Yes.
I might skip a few things then. But so here are a few past results. So we have when you whisker all vertices, you get Koszul. We have when you whisker a vertex cover, you get Koszul for all symbolic powers. And when you whisker the cycle on a unicyclic graph, so it's just a graph that's a single cycle with a bunch of edges coming off of it, then all symbolic powers of the cover ideal are Koszul. So we've got a lot of results. And these are powered by some of these, by a couple of constructions. So in 2016, Fakari introduced this graph GK, which you construct by taking your original graph, copying each vertex k times, and then adding edges so that the second index that you introduce, so down here, so you introduce a P and a Q, so that P and Q are at most k plus 1. And this is a really cool construction because basically he shows that the polarization of the cover ideal, of the symbolic power of the cover ideal of the graph is the cover ideal of GK. So now I just need to show that GK is vertex decomposable. And I'll get this is Koszul. So what does this look like? What does this all mean? Start with G. Copy each vertex 3 times to get G3. And then connect the edges. So you can see I don't connect 2 to 3 because 2 plus 3 is 5 is too big. I also don't connect 3 and 3 for the same reason. This got loosened a little bit, a slightly more general result by Kumar and Kumar, which basically said instead of doing it to the whole graph at once like Fakari did, do it to each edge independently. So for each edge, you introduce a k, copy the vertices of that edge k times, and then connect those new introduced vertices under the same restriction. Then, union all of those things together, you get this new graph GK vector. And that's a really cool construction because you can get a much more, a much looser construction, so it's much easier to work with. That's a lot harder to break, basically. So here's a quick example. Start with the same graph, label your edges, then G1322. Edge 1 is copied once, so it's just at the original edge. Edge 2 is copied 3 times, so this is exactly what it looked like in Fakari's graph. Edge 3 and 4 are copied twice, so I only need 2 copies of these vertices and connect it appropriately. And this is a really, additionally really great because if you just let all of the, if you copy all of the edges the same number of times, you get GK. And lastly, here's a useful tool by Selvaraja for proving vertex decomposability of a really complicated graph. So instead of having to do this sequencing thing, I can just prove these 3 for a sequence of vertices. So Zi is always a shedding vertex. When I delete my sequence and the neighbors of the next vertex, it's vertex decomposable. And when I delete my whole sequence, it's vertex decomposable. Then the original graph is vertex decomposable. I'm gonna skip that part. So I'm gonna use that Silva-Raja's theorem to basically prove what I want to prove. So here's our first lemma. This is the first really hand-wavy thing. Basically what this says is that if I whisker a vertex in G, when I take GK vector under certain restrictions, every time I delete one copy of that whiskered vertex, x1 is what I called it here, then the next vertex is whiskered. You can see what that means here. So in this graph, I have whiskered the original graph the original vertex x1. So these blue edges are the shadows of the whisker. So if I delete x1, I get this graph, and now x12 is whiskered. So the second vertex in my sequence. And that's what that theorem says. Like just as I go along, the next vertex will always be whiskered. So the next vertex will always be a shedding vertex. This theorem basically says if you delete enough vertices, it's equivalent to an incident edge never having been in your graph, or reducing the number of copies of that edge by so many terms. So again, you can see that here. If I delete both x1 and x2, or x11 and x12, then I delete this whole portion of the graph, which is like those edges never existed. I get some isolated vertices, yeah, those are easy to deal with. But I basically just remove a portion of the graph by deleting enough copies of this vertex. And this corollary basically says the exact same thing, but for vertices. So if I delete all the copies of my vertex, it's like that vertex was never there. Which is all really, really useful for breaking stuff like I want to do. So here's our main result, and this is probably gonna be the last thing I talk about. So I pick S to be a cycle cover. So what a cycle cover means is that every cycle has a vertex in this subset of vertices. Or equivalently, if I delete this subset, I get a tree or a forest, if you know anything about graphs. Then for any tuple where my whiskers are copied at least as many times as the edges around them, G union the whiskers, so the whiskered graph is vertex decomposable for that K vector. And the corollary to this is let all of the Ks be the same, then you get the cover ideal as Koszul. So this whiskering forces symbolic powers, all symbolic powers of the cover ideal to be Koszul.
You have a couple of minutes.
Cool, I'll use those couple of minutes to just do this. So if I start with this graph, this is G3 of that graph, which is the same as, I guess, G3, however many threes. So if I delete x1, now x12 is whiskered. If I delete x12, now x13 is whiskered. So my sequence of x11, x12, and x13 are all shedding vertices like I want. If I delete all of these vertices, then I get the G3 of this graph, which is a tree, so all symbolic powers are vertex decomposable like I want. And then the last thing from Selvage's theorem I need to prove is that if I start deleting neighbors. So if I delete the neighbors of x1, I get this, which is vertex decomposable. Just a bunch of isolated vertices. If I delete x1 and then the neighbors of x2, I get that. That's just a couple of edges, vertex decomposable. And if I delete x1, x2, and the neighbors of x3, that is G2 of this graph. So it's vertex decomposable. And another way you can look at this is that doing this construction in this way by inducting on the number of cycles, I always break the number of cycles. Or I always reduce the number of cycles by at least one. So no matter how I start deleting things, I'm always going to reduce the number of cycles. So by inducting on the number of cycles of the graph, I get vertex decomposability. So where I'm going to take this, or I would like to take this, is if there's a smaller subset. There's some evidence of that for certain cycles. And what are necessary and sufficient conditions on S? So I've gotten some necessary conditions, but I'd like some sufficient conditions as well. And that's all. Thanks.